Hello and welcome to Boolean Algebra Level 3. 3 input NAND gates only with no inverters, and we've got to express that. Well, first thing to note there is that it's an ideal application of the extension of De Morgan's theorem, which, if you haven't come across it before, says that not x or not y or not z is equal to not x, y, z. But you can extend De Morgan's theorem to any number of variables in a similar way. So here we could see that not b or not e or not c and not d is just equal to not of b, e, and then not c or not d. Well, we've got one 3-input NAND gate there, but we've still got this OR gate there, which we can get rid of with another application of De Morgan's theorem, and that would just give us not b, e, and then not c, d. Well, we've got one 3-input NAND gate, but this is not a 3-input NAND gate. This is a 2-input NAND gate. If I was to draw this out as a circuit, I would have a NAND gate here with b into one input, e into another input, and the third input would be this term here, and that is the output of a AND gate with c going in one terminal, d going in one terminal, and, well, I'm only allowed 3 input NAND gates, so I need to have another input there. And the trick here is to just set it equal to 1. Because with this set to 1, that behaves exactly like a 2-input NAND gate. So that should do. Just express it as not b, e, and then not c, d, 1. And I need the 1, otherwise it's not a 3-input NAND gate here, it's only a 2-input NAND gate. I'll show you. If I wrote this as not b, e, and then not c, d, it would be wrong, because this is not a 3-input NAND gate. But if I put a 1 in there as well, it's fine. That's the trick that might catch you out the first time you see those ones. Let's see if there's a different type. Okay, this is a simplify, but it's only one variable. There's only one g variable in there. So there's only 4 possible things this can be. It can either be g, or 0, or 1, or not g, and that's it. Which is it? Well, the first 2 not signs here cancel out, so that would be just g or not. Well, 1 and g is just the same thing as g, because 1 and anything is just anything, so that's just that. And we have g or not g. Well, it doesn't matter what g is. G or not g is always equal to 1. Because if g is 1, that would be 1 or 0, which is 1. And if g is 0, that would be 0 or 1, which is also 1. So this just simplifies down to 1. This one, NOR gates with no inverters. And it's currently just an inverter and a AND gate. So, again, we get rid of the AND gate by applying De Morgan's theorem. And that would give us not of not s or u. And then we've got one NOR gate there, but this is not s. If I was to write that out as a circuit in terms of gates, what that is saying is it's NOR, not OR, of u into one input, and the other input is not s. Well, I'm not allowed to use inverters. I'm only allowed to use NOR gates. So I've got to make not s from a NOR gate, which actually you can do quite simply. I could do it like this. Attach both of these two inputs to S. And then that would behave like an inverter. If S was a 1, the output here would be 0. If S was a 0, the output here would be 1. That would work. So I would write that as not of U or not of S or S. And I should be fine. Not of U or not of S or S. Fine. Okay, another one. We've done one like that before. We've done one similar to that before. And this one, that's a simplification, but we've now got two variables, m and n. So there's a wider range of things this could be. But noting that we've got two nots here, and two nots like that cancel out, that's just equivalent to saying not m or n and m. And if I multiply out those brackets, I would get not of m and m or n and m. Well, m and m is just m. If m is 1, that is 1. If m is 0, that is 0. So that would just be m or n and m. If m is 1, then this term on the bottom here is 1. If m is 0, then this term on the bottom here is going to be 0. It doesn't matter what n is, n and 0 is going to be 0. So if m is 1, this would just be equal to 1. If m is 0, this is equal to 0. So that's just not m. N is irrelevant. Is that enough? Yeah, that's probably enough. Over to you.